Right. Hi, everyone. We're going to wrap up our discussion of a solubility equilibrium by relating the solubility equilibrium with reaction for complex ion formation. I'm going to first just give you a brief description of what complex ions are. Complex ion is just a transition metal ion that is forming what we call a coordination complex with other molecules that are called ligands. So these ligands are either anions or neutral molecules that have free lone pair electrons. Transition metal has a high positive charge, for example, iron 3 plus, manganese 4 plus, cobalt 3 plus, all of these transition metal ions are small and they have a lot of positive charge on. So they need electrons to neutralize those positive charges, and that's what the ligands provide. Here's a couple of examples of complex ions. This one in particular has copper as the transition metal ion, and it has 4 ligands surrounding it. Each one of the ligand is ammonia, and you might remember ammonia has a structure that looks like this, has a lone pair on the nitrogen. That lone pair is what's being used to form this coordinate covalent bond with the transition metal. Here's another example of complex ion, in this case formed by cobalt 3 plus, with 6 different ligands. 4 of these ligands are your ammonia ligand again, and then 2 of the ligands are actually chloride ion. The number of ligands that will bond to a particular complex ion could be usually 2, 4, or 6. There will be a table later on that's to help you figure out how many ligands are bonded. Now, one of the most important features of complex ion is that they have very distinct colors. So these two here are actually corresponding to the colors of the species that we just discussed. So this one is the color of that copper complex ion, and then this green one is the color of the cobalt complex ion. And they have all these colors because the transition metals happen to absorb light in the visible region, and that's what allows the colors to appear. As you see, there is a number of ligands that could bond to the transition metal, and the bonding of each of these ligands goes through specific steps. So for example, there is a complex ion that is between silver with 2 ammonia, and the complex ion looks like this, which is AgNH3 with a plus on it. And the way you figure out the charges on these complex ions, combining the charges on the metal ion and then the ligand. In this case, the ligand is neutral, so silver has a charge of +1. That's why the entire complex ion has a charge of +1. Now, because there's 2 ligands here, the process of the formation of the complex ion goes through 2 steps. So the first step is just silver with 1 of the ammonia coming in. This is a reversible reaction, and it's going to form this first complex ion, which is AgNH3 plus. That reaction has its own K. As you can see here, the K value is pretty large, so that's a favorable reaction. And then that product that's formed in the first step is going to bond with another ligand to form the final product, which is AgNH3 plus, and that one also has a favorable K. Okay, so when we do calculation, we don't treat this reaction separately. The reason is because each one of the steps has a large K, and so each one of this reaction is really sort of a limiting reactant type reaction. So whenever we have this type of situation, we're going to have to work using the large K type approach where we have to add all the reactions together. And when you do that, you get this overall reaction, which looks like this. The K of this reaction is just the top 2 reactions K multiplied with each other. So K1 times K2. We call this K, KF, or the formation constant for the formation of complex ion. Large K approximation means that we add both reactions together. We assume the reaction goes to completion, and then afterwards to figure out the concentration of the species that are in the middle, which is that first complex ion, and then the silver, we're going to have to work backwards. We're going to have to reverse the reaction. So an example here is, say we have 0.1 mole of AgNO3, and it's dissolved in 1 liter, 1 molar of NH3. So we know that the Ag and the NH3 can form a complex ion. The question is, what's the concentration of the Ag plus and the AgNH3 plus, which is that first species that was formed during the formation of the complex ion. You don't start with each of the reactions, but what you do is you add those 2 reactions together. So when you add the 2 reactions together, what you get is this reaction right here, right? Ag plus 2 NH3 goes to AgNH2 plus. So this is just the overall reaction once you add reactions 1 and 2. The K is the KF that we were given earlier. So because it's large K, we're going to figure out if there's a limiting reactant and then calculate the change based on the limiting reactant. In fact, in this case, the silver is the limiting reactant because it's a smaller number. The ammonia is 1 mole, so we're going to have negative 0.1 and negative 0.2 here. 0.2 because the ammonia is a 2-to-1 stoichiometry with the silver. And then we have plus 0.1 on the complex ion. And at the end, we have 0, 0.8, and 0.1. Now, the key here, of course, is to remember that that's not really zero, we can figure out how much it is by reversing the reaction. So that's what we're going to do in step 2. We reverse the reaction to calculate the silver ion concentration. I started with these numbers here for my initial value, which is just the same exact set of numbers that I have at equilibrium in my first reaction. And then because I'm reversing this, my K is just going to be 1 over Kf, which is this number right here. So it's a small k, which allows us to express the change as minus x plus x and plus 2x. And so this is the equilibrium concentrations that we have. We set those equilibrium concentration, which has this expression, right? X 0.8 plus 2x squared over 0.1 minus x equal to the K value of that reverse reaction, which is a small k. We can then use our small k approximation here to help simplify some of these calculations. So this can go away, that can go away. So the expression then becomes just this, x times 0.8 squared divided by 0.1 equals to the K value. And if you solve, you end up getting 1.42 times 10 to the minus 8. That's the silver ion concentration. Okay, so remember that there's 2 steps in the formation of the complex ion. First step was formation of intermediate is AgNH3+ plus. And what happens if we want to calculate the concentration of that? Well, so what you need to do is you're going to need to reverse one of the steps that has that speed, which is this step 2 right here. Okay, so you're just going to need to reverse that. And I'm showing that example right here. So I'm going to take that reaction 2 and I'm going to reverse it so that it goes from the full complex ion, this one right here, forming the intermediate and then one of the ligand. So it's sort of like imagining that complex ion breaking apart or dissociating to form the intermediate species and one of the ligand. The numbers that we're going to put in here would be the numbers that we have from that first table, which is this one right here. Okay, I have 0 of that intermediate species, again, because that reaction has a large K originally, so it's assumed to go to completion. And we're basically solving it exactly the same way as the work that we did for solving for the silver ion. The only difference is that the K value here is not 1 over Kf, so we're just going to do 1 over K2, K2 being the specific equilibrium constant for the conversion of that intermediate into the final complex ion. So it's just that step right there. Okay, and then so once you do that, you'll be able to solve for x the same exact way as we did here for the silver ion. It's obviously pretty important to know exactly what kind of complex ion could be formed with a specific transition metal and a ligand. So how do I know whether I'm going to have a 2 ligand, 4 ligand, or 6 ligand type complex ion? Well, you don't need to know that. It's actually a little complicated to kind of figure that out on your own. So what I'm going to do here is just have a table, which I'll provide for you during test. So you're able to look at this table and figure out what kind of complex ion could be formed. So for example, if the question shows silver and ammonia, immediately you will see that the formula is AgNH3+ so you know that there's 2 ligand in this particular complex ion formation. Whereas if you're given zinc and hydroxide, for example, you can immediately see here that there is a zinc with 4 hydroxide bonded to it. So that's the complex ion that's going to be formed. Use this table to help you figure out how many ligands are supposed to be bonded to that particular transition metal. And of course, the last column here shows you the actual Kf value, which is the overall K value for the formation of the final complex ion. Keep that in mind. So that would be the product of all the individual Ks that lead up to that overall reaction. What I want to do here is then connect this complex ion formation reaction to the solubility equilibrium that we've been discussing. Some of these salts, they're insoluble. The cations of that salt that are produced when the salt dissolves is actually also a transition metal. So as a result, if we provide the appropriate ligand, we can force the reaction to shift to the right. And what I mean is the following. So for example, if I have that same situation here, AgCl now, which is an insoluble salt, it has its own KSP. So it's going to produce Ag plus and Cl minus ions, but very small quantity of that, right? Now, what happens if I start adding ammonia to the solution? Well, we know that ammonia, based on that problem that we just worked on, is going to form a complex ion with silver to produce this AgNH2+ complex ion. This Kf is much larger than 1. The KSP is much smaller. But if you were to combine these two reactions, as you might see from Le Chatelier principle, this reaction is going to be much driven to the right because the Kf is large. And so therefore, that helps pull down the concentration of Ag+. If the concentration of Ag+ goes down, that means more AgCl has to be dissolved in order to get back to equilibrium for that KSP equilibrium, okay? So what I'm going to do here is show you an example of how to do the actual calculation to figure out how solubility is changed as a result of the availability of a ligand that can form a complex ion with the transition metal. So let's take a look at the problem. It says compare the solubility of AgCl in water and in the presence of 0.1 molar ammonia. Okay, so literally we just want to see if I just put AgCl in water and I have AgCl now in a solution of ammonia, what would the difference be in solubility? So we can do the calculation pretty easily in water. All we need to do is find the KSP value, which we can look up. It's 1.8 times 10 to the minus 10. And the calculation is just going to be 0 at the beginning, and then at the end you have X of each of the ion. You set that equal to KSP here, and you're able to find that the X is equal to 1.34 times 10 to the minus 5 molar, which is the same as the solubility of AgCl in water, okay? Now, the more complex calculation is when you have that ligand present, which now allows you to have a second reaction that's going to be coupled to your solubility equilibrium reaction. So to calculate that, we're going to start again with the solubility equilibrium. Then we're going to add this second reaction, which is the formation of the complex ion. And the reason we write it this way is because, again, we know that second reaction has a large K. So it's going to consume the silver that's produced by the first reaction. And as a result, that's going to force the equilibrium to shift to the right. So how do we actually do the calculation? Because we have a large K situation here that follows the small k, again, we can't treat this as independent reaction, because whenever we have these type of situations where the second reaction is a large K, that means the whole thing is tied up together. So you have to add the reactions together, which is what I did here. So when I add the reactions together, certain things cancel away, and that's the Ag plus. So the overall reactions look like AgCl solid with 2 ammonia forming the complex ion, and Cl minus, because the Cl minus concentration directly comes from AgCl. There's no other compound that produces Cl minus. So if we know the Cl minus concentration, that concentration should correspond to the solubility of the silver chloride itself. So now I'm going to do some calculation. It tells us that there's 0.1 mole in 1 liter of ammonia. And then we don't have the complex ion, we don't have Cl minus at the beginning. Notice that I'm not doing anything with that solid column because solids don't factor into my K expression. I'm going to lose 2x, x, and x. Well, why am I using x? Well, if you were to add the two reactions, then the K of this reaction is going to be the product of KSP times KF. So when you do that, you get this number right here, which is a small k number. So because it's small k, you can't assume completion. You have to just calculate it directly, just as we did before, okay, with x. So our final equilibrium concentration is 0.1 minus 2x, x, and x. We set that whole expression equals to k. So x squared, because it's x times x, divided by 0.1 minus 2x squared, because the coefficient is 2. And that allows us to solve. We could use the small k assumption and then check if the assumption makes sense. Or since we have square on the right side for both expressions, we might as well take square root of both sides. Mathematically, that's not too hard to do. And so we get this number on the left side, and then we get the expression x over 0.1 minus 2x on the right. From here, we can go ahead and just solve for x, which is what I did here. I did a little algebra and find that x equals 0.004086 or 4.1 times 10 to the minus 3. That's your Cl minus concentration, but remember that that also represents the solubility of AgCl. Now, the key conclusion I want you to compare is this number right here that we just got, 4.1 times 10 to the minus 3, and then compare that to the number we got earlier, which is the solubility in water. In water alone, it's just 10 to the minus 5. Now with the presence of ammonia, it's 10 to the minus 3. So the solubility of the AgCl has increased by about 100 times by having that ligand around. So we have made this insoluble salt, AgCl, a lot more soluble by adding the ligand in our solution, okay? And you might wonder, why is this relevant? Why is this important? Well, in selective precipitation, we need to use this tool to help us make certain ions soluble while keeping some others precipitated, so we can separate them out.